amides. Remember, an amide is where we have R, C double bond O, NH2, or NHR or NR2. In an amide, they're very abundant naturally. If I have a protein, proteins are linked by amides, right? Here's C double bond O, NH, and then CH2R, then again, C double bond O, NH, right? It's a polymer, right? It's essentially a polyamide, right? Where we have that C double bond O, NH linking all those segments of amino acids, like we talked about before. A lot of antibiotics. Here's benzyl penicillin, right? One of the penicillins. It has a couple of amide groups in it. Sort of interesting because it has an amide as part of this four-membered ring that's fused in right here. So interesting structure. Here's a ribonucleotide, has two amide functionalities in it right there as part of that ring. So several biological molecules have amide functionalities in them, many times because they were biosynthesized from amino acids, which have these, which can have these amide groups. So the best way to prepare an amide is with an acid chloride, and then the appropriate amine. So be careful to note that one H is removed from the amine in the reaction because one of nitrogen's three valences goes into the carbonyl. So if I want a primary amide, I have to react it with ammonia, with NH3. A secondary amide comes from a primary amine, right? A tertiary amide comes from a secondary amine. Right, because we're essentially adding a carbon bond to nitrogen. Tertiary amines cannot react to make amides. We have to lose one of the H's. So amides, let's talk about hydrolysis of amides. Remember, since amides are the least reactive of all the carboxylic acid derivatives, I can do hydrolysis, but it takes harsh conditions. We have to reflux it in boiling aqueous acid or base. The mechanism is very similar to the other hydrolysis reactions that we've seen. If I do this in acid, remember what happens first. The carbonyl is protonated, water attacks. We have a proton transfer, right, to make this NH2 into an NH3 plus leaving group. It's kicked off, and then there's an acid-base reaction right here, where I regenerate hydronium by removing the H, and we kick out a neutral NH3, but there's a acid-base reaction, right? Because hydronium is a stronger acid than NH4 plus is. So we end up with NH4 plus and water as products of this. Basic hydrolysis is a very simple mechanism. Hydroxide adds, okay? O minus comes down and kicks out NH2 minus, okay? Again, an acid-base reaction will occur then because the carboxylic acid is a stronger acid than the amine, which is pKa of 35 or something like that. Okay, so very similar thing that happened with basic hydrolysis of esters. Our product is a carboxylate ion. Okay, so really any basic hydrolysis gives you a carboxylate ion because the resulting carboxylic acid is protonated by the basic leaving group. This reaction, this base catalyzed hydrolysis, though, is especially difficult because NH2 minus, right, is a pretty poor leaving group. So we're kicking out an actual negative. The only reason that this can actually happen is because NH2 minus can pick up a proton from the carboxylate. So the reaction will be slow, but under pretty harsh conditions, you can actually get product. Right? The equilibrium is shifted towards the product because of this favorable acid-base reaction that happens at the end. So let's talk about reduction. If I have an amide and I react that with lithium aluminum hydride, something kind of interesting happens. It's a little different. We don't have this N group over here is not our normal leaving group. Okay? It actually converts the carbonyl into a methylene, into a CH2. So if I have this N-methyl amide with lithium aluminum hydride, I get just an amine. Okay? We have a CH2 next to the N. So this mechanism has a key difference compared to ester reduction with lithium aluminum hydride. Right? Get these two mechanisms next to each other as you're studying and actually compare them. So look what happens. First step is the same. Hydride adds to the O minus, but then our NH2 is not the leaving group. O complexed with aluminum, right? That's actually a better leaving group than NH2 minus, right? Remember, because I told you before, NH2 minus is a poor leaving group. That's one of the reasons amides are so unreactive, especially in basic conditions. They're tough reactions. So since NH2 minus is such a poor leaving group, it actually kicks out the O aluminum. Okay, so it's an aluminum stabilized O minus. So if we look carefully at what we get here, that makes a CN double bond, right? Which hydride can add to again, okay, giving us an amine. So we have this intermediate iminium ion. So make sure you know this mechanism. It's very important. Okay, especially because of its weird step here where NH2 is not the leaving group. It's the O aluminum complex that leaves. So let's actually write that up here. This is actually, and we'll see more of this in the amine chapter, but this is a good way of forming cyclic amines from lactam. A lactam is a cyclic amide, just like a lactone was a cyclic ester. If I do a ring closing reaction making this lactam, I can use lithium aluminum hydride to get rid of the carbonyl, and we have just a regular plain old amine. I could envision making this lactam. Remember, since amides are formed from amines, right, and carboxylic and acid chlorides. So if I have an acid chloride and an NH2 in the same molecule, it'll do a ring closing reaction to make an amide, but since it's cyclic, it's called a lactam.